courses on fundamentals of electrical engineering. We were on the fourth module. We were doing signals and systems, and therein we were mostly focusing on continuous time systems. Before we move into discrete time systems, this is the last session, which belongs to continuous time systems in general and linear time invariant systems as well. Moreover, we found the distinction between the linear and the nonlinear systems, I suppose, by now. The time invariance has also time varying situations or scenarios. We also had in fact, we were discussing all causal systems because all real systems are causal. We also talked about the stable systems, and perhaps the most intuitive kind of operation that you can do on signals, which is the convolution. So as we mop up some of the questions that were not yet covered, we of course will have to do a little more of convolution as well, because that is all pervasive, is what I feel when I look at the fundamental questions that are coming in the GATE examinations. Okay, so let's move to the first question. So let's go to the first problem. As was mentioned earlier, we are doing a sort of a mop-up of all the different problems that were not covered, or what are the different types of problems that were not covered. But of course, in the linear time invariant systems, for linear time invariant systems in the continuous time domain itself. Okay, so let's look at the first problem. For the system 2 by s plus 1, the approximate time taken for a step response. Okay, so it's a step response, or in other words, the input is going to be a step input, okay, to reach 98% of its final value. Okay, so there are a few aspects that we need to remember for such a problem. One, first and foremost, this system is now attempting to give the output such that it follows the input to the extent possible. Okay, but of course, if there is a time delay, as was mentioned earlier, the time delay will be given by the 1 by s plus 1 quantity. Okay, so we see that 2 by s plus 1 is the same as equal to 2 into e raised to minus t. Okay, however, when you're inputting a unit step input, what is going to happen is that you're going to get the same on the output. Okay, so we see that now we have the step response reaches 98%, and so what it does not reach is going to be 2%. Okay, so this 2% is what has to be covered by the time delay quantity. So in other words, we can say that 2% or 0.02 is the same as equal to e raised to minus t. Okay, so that's the difference between the two. This is another interpretation of the same problem. Okay, so now if 0.02, or in other words, it can be seen as equal to 0.98 is equal to 1 minus e raised to minus t. So we are removing 2 because there's no meaning in it, because we are the function, the system is trying to rise to the input level, which is equal to 1. Okay, so because it's a unit step input, so we have 98% or 0.98 same as equal to 1 minus e raised to minus t, e raised to minus t being obtained from the Laplace inverse of 1 by s plus 1. So we see that we are arriving at the same aspect or the same situation that was mentioned earlier. There is still a little more to go. There is 0.02, and that is achieved by e raised to minus t. So 0.02 is equal to e raised to minus t, and t is required. How do you do it? Take the natural logarithm on both sides. So we see that the natural logarithm of 1 by 0.02. Why? Because you would prefer to have 1 by e raised to minus t or e raised to t. Okay, so t, the natural logarithm of e raised to t is t. So t is equal to ln 1 by 0.02, or ln, and the natural logarithm of 50, which is equal to 3.91. So from amongst the 4 options, the approximate time is asked. So we see that 3.91 matches C, or 4 seconds, most appropriately. Okay, so let's go to the second problem. A low pass filter with a cutoff frequency of 30 hertz. Okay, so it's a different problem, no doubt. Low pass filter with a cutoff frequency. So what do you mean by a cutoff frequency of 30 hertz? That is, the frequency below 30 hertz is going to be passed by this low pass filter. Okay, because it is passing the low frequency. Okay, it's cascaded with a high pass filter. So it's simple. It's similar to a convolution, no doubt about it. And what does the high pass filter do? It passes frequencies with the cutoff frequency of 20 hertz, that is beyond 20 hertz. Okay? So 20 to 30 hertz is being passed. This is the situation that we have. The resultant system of filter will function as, okay, so it's a band pass filter, no doubt about it, and passes frequencies from 20 to 30 hertz. But of course, there could be some 3 dB levels. Okay, so option D tells us that from amongst the 4 options, this is the most correct answer. Okay, so let's go to the third problem. Continuous time system is described by yt is equal to e raised to minus xt. So here we have to be very careful because the numerical value is asked, okay, where yt is the output and xt is the input. Yt is bounded. So what do we mean by yt being bounded? Yt is generally bounded if it's a stable system, if xt is also bounded. Now we have a problem here in the sense that we have the system yt explained as equal to e raised to the absolute value of xt. So if xt is negative, it still becomes it's still e raised to minus xt is still positive. Okay, yeah. So and what is the speciality of e raised to minus xt is that whatever be the value of xt, be it positive or negative, since we have taken the absolute value, it's going to be always e raised to minus xt, which means a decaying function. So whatever be the value of xt, we are going to have a bounded output. Okay, so this is and that's what is asked. A continuous time system is described by yt is equal to e raised to minus x minus absolute value of xt, where yt is the output and xt is the input. Yt is bounded only when xt is bounded? No, because even if xt is not bounded, even if xt is infinity, we know that e raised to minus infinity is 0. Okay, only when xt is non-negative? No, because the negative part has been taken care of. Okay? Only for t greater than 0 if xt is bounded for t greater than 0? No, not at all. And then, of course, another aspect is that we don't take the time the time axis into consideration here. Only the numerical value of e raised to of xt is going to be taken into consideration. So the negative time axis or the positive time axis is not of concern. Okay, even when xt is not bounded. This is exactly the true answer. Why? Because of the negative exponential. So let's, or the negative exponent for the exponential. Okay? So let's move to the fourth problem or the fourth question, the impulse response of a causal. So a causal system means that the output is always going to be only after the input has been caused or initiated. Okay, that is at t equal to 0. Okay, or beyond. Okay, a linear time invariant system. So linear time invariant. So that's the general system that we prefer to analyze. Why? Because linearity gives rise to superposition. Okay, system is given as ht. Now consider the following 2 statements. Statement 1, principle of superposition holds. That you just mentioned right away. And statement 2, ht is equal to 0 for t less than 0. That's a causal system. So both statements are true. Which one of the statements, following statements is correct? So from amongst the 4 options, 1 and 2 is wrong, 1 is correct, 2 is wrong, 2 is correct, 1 is wrong, 1 and 2 are wrong, 1 and 2 are right. Okay, so 4th option. Okay, so without doubt, we pick up the 4th option. Moving to the 5th problem for linear time invariant systems. Okay, so we are mostly discussing, as I said, linear time invariant systems that are bounded input, bounded stable. Which one of the following statement is true? Bounded input, bounded output systems, the condition that needs to be abided by or satisfied is that if you take the integration from minus infinity to plus infinity of the impulse response, whatever be its magnitude, ht, that is the absolute value, and then if you integrate it with respect to time, it should be bounded. Okay, so this is the only condition that we have. Okay, and so let's see if this is given. The impulse response will be integral but may not be absolutely integral. That's not true. The unit impulse response will have finite support. That is, it exists only within a particular period of time. That's also not right. Okay, because that's not true. The unit step response will be absolutely integrable. Okay, so that's not the condition. The unit step response. So when you talk about unit step response, you are taking the integral. Okay, of the impulse response. Okay, and that's done here, and that has to be bounded. Okay, so that's exactly the thing that we were talking about when we said that minus infinity to infinity ht dt should be bounded. Okay, so that is when you take the step response is exactly the integration of the impulse response. Okay, that needs to be bounded. Okay, so option D is right in this case as well. 6th problem. The impulse response of a continuous time system is given by ht equal to delta t minus 1. That is, the impulse is delayed by time, one time unit. And we also have another term, or there are two constituents for the impulse response. The other one is delta t minus 3. What does it mean? That we have an advancement of the impulse response of the impulse, okay, as a part of the impulse response, okay. The value of the step response at t equal to 2, okay. So what do we have? We have two components for impulse response. As we did in the previous problem, we can take the integral of both the components and add them together, okay. So that gives you what is called as the step response, because the value of the step response. So what do we have here? If you integrate the impulse at t equal to 1, you get a step input starting at t equal to 1, okay. And then to that, so it continues, but then at t equal to 0, you have another impulse coming in, and which you integrate again, so you get another step input superimposed on the above, okay, because there's a plus term there, okay. So we are having two impulses, one above, two unit step responses, one above the other, and at t equal to 2, okay. At t equal to 2, we see that the second step response has not yet arrived, so it's equal to 1. So from amongst the options A, B, C, D, we pick up B, because that tells us that we have a step response equal to 1 at t equal to 2, okay. At t equal to 3, we have at t equal to 3, we again start to have a larger quantity of 2. So moving to the seventh problem, again, as I said earlier, these are mostly little different from the previous types of problems. Here we are given a few diagrams, okay. So I suppose the diagrams are clear to you by sight. We have P telling us giving us what may be called as a overdamped diagram. Then we have Q, which is telling us about a step response, okay, because it is similar to 1 minus e raised to minus t. With the magnitude of perhaps, then of course RT is, and then it's an oscillatory circuit, and then we also have an underdamped version, which is S, okay. So R is oscillatory, S is underdamped, okay. So let's look at the transfer functions. 1 by S into S plus 1, so that will give you us 1 into 1 minus e raised to minus t. This should be clear to you immediately. So we have what we can see that it matches Q, okay, or A matches Q, okay. Then moving on to 1 by S plus 1 whole square, that is where we are having a t and a e raised to minus t coming together. So we have an overdamped situation as is given in B, okay. Then we have 1 by S into S plus 1, or S square plus S plus 1. So that can be converted into S plus alpha whole square plus omega square, okay. And so we see that we are having what is called as a e raised to minus alpha t and a sine or a cosine, okay. Of course, now it's a case of omega, so we can say that a sine quantity array, sine beta t into e raised to minus alpha t. So that is a underdamped version. So we see that S matches C, okay. Finally, we have 1 by S square plus 1, which is a pure sinusoid in its Laplace inverse version. So we see that we have R as this as matching to the transfer function given by D, okay. So as simple as that. I hope all the different very important diagrams are also very clear to you, okay. So we come to the last slide and the last problem, which is 8. What does it tell us? The transfer function of a linear time invariant system is given as Gs is equal to 1 by S square plus 3S plus 2. Okay, the steady state value of the output. Okay, so here we are having steady state value, or in other words, this is the same as is the final value theorem. Okay, the output of this system for a unit impulse input applied at time equal to t equal to 1. So we are seeing that we are having an output given by the Laplace transforms of HGS multiplied by XS, where XS happens to be the input, and so unit impulse was applied at t equal to 1. So its Laplace transform is the same as equal to 1 into e raised to minus s. Okay, so we have GS 1 by S square plus 3S plus 2 multiplied by S into multiplied by e raised to minus s. Okay. Now to get the final value, take the limit after multiplying the combination by s, and take the limit as s tends to 0. So we see that in we have e raised to minus s is equal to 1, and in the denominator we have all quantities disappearing except 2, but then the s at the top remains. So we see that when s tends to 0, the limit is going to be equal to 0. Okay, so we have option A as the best solution. Okay. On the other hand, if it was the initial value theorem, then we would have had to take the s quantities outside and get them cancelled. Otherwise, again, it would have, you would see that you will be landing up with infinity, where you will not be able to solve the problem. Okay, so I suppose by now all different types of problems in linear time invariant systems, causal systems, as also stable systems are more or less clear to you in the continuous time domain. Next week, go into the discrete time domain. Thank you.